So our next speaker is Alex Auld from the University of Sheffield, who's going to talk to us today about development of ChapSim2 for modelling magnetohydrodynamic turbulence.
Hello, I'm sorry, more magnetohydrodynamics, but it's quite different what we do. So I'm from the University of Sheffield. My name is Alex Auld. I'm a PhD student, and I just started my second year of study. So the application for magnetohydrodynamics, I should have said we're part of the CCP for nuclear film hydraulics. So we're focusing on the application for fusion reactors. So I'm going to give a quick rundown of fusion reactor design, our magnetohydrodynamics in fusion, and then go into our numerical model and our current work. So this is a schematic of a typical fusion reactor. You have a large donut in the middle, which is plasma contained at 150 million degrees Kelvin, which is contained by a very strong helical magnetic field. So the fuel for our plasma is deuterium and tritium. Deuterium is very readily available, but tritium is a radioactive isotope that decays very quickly. So we don't have any tritium effectively to run our fusion reactors with. So our fusion reactors need to make their own tritium. So we do that by surrounding our reactor chamber with lithium and using a high neutron flux from our plasma to split lithium into tritium. So essentially, our reactors are made to make their own fuel. And so that means that we have a blanket which is just sort of behind the first wall of our fusion reactor. So you can either have a solid or a liquid metal breeding blanket, but there are a lot of advantages to liquid metal breeding blankets, such as the excellent coolants. So we have the highest sort of thermal efficiency of up to 45%, which is excellent for a power station. And they also make the most tritium, which solid breeders don't make very much. That's very marginal. But we have some unfortunate things, which are the reactivity of lithium, which is it tends to eat everything or set it on fire. But on fluids, guys, that's not my problem. And MHD effects, which is my problem, unfortunately. So we have some rather simpler equations, fortunately, than the last guy with neutron stars. So because we're working at small length scales with a fluid which has very high magnetic diffusivity, we can essentially ignore the induced magnetic field by the current within the liquid metal, which simplifies our MHD equations to those on the right. So we can use Ohm's law. This is for electric current density. We can apply our conservation of charge over our domain to Ohm's law and find a Poisson equation for our electric potential. And essentially, when we have our fluid moving through our magnetic field, it induces a current, which creates a Lorentz force, which is a body force on the flow. So these are all orthogonal relationships. So essentially, when you have a magnetic field moving across the flow, you have a body force that actually opposes the motion of the flow. So this is the momentum equation with an additional term for buoyancy, as our flows are very strongly heated, and our Lorentz force there, as well as the energy equation, continuity equation. So in fusion reactors, we have a very strong magnetic field of the range of Hartmann times 10 to the 4. A Hartmann number is the strength of our electromagnetic force relative to our viscous force within the fluid. So 10 to the 4 is a very high number. And we have a very high heat flux. Our fields are unfortunately multidimensional. So we have the plasma itself generates a poloidal magnetic field, which is transient because we tend to pulse the plasma. And we have a very high heat flux, which is also transient. So in our breeding blanket, we have electrical coupling between channels, and then our usual difficult geometries and different orientations of flow. So lots of complicated stuff going on, essentially. So in an isothermal flow, our magnetic field tends to laminarize everything past quite a low value. So our velocity profile on the left here is an isothermal flow. But the electrical boundary conditions can completely change that because they change the structure of the electric field within the flow. Then we end up with sidewall jets, which are the figure on the right. And then the other thing that we have happening is Joule dissipation. So that's essentially the heating of the fluid due to the electrical resistance of it. It's like how wire gets hot when you put a current through it. So that provides an additional sort of kinetic energy sink, which is sort of an alternative to viscous dissipation, which is our usual kinetic energy sink in turbulence. Yeah, and so essentially we have some complicated flow features in our channels. The body force leads to very thin shear layers along the walls. We have sort of transitionary turbulence, which needs a long spatial domain. And then if we're modeling with liquid metal, it has very strong thermal diffusion, so we need to have a very small time step. So all of these things combine to be a very numerically stiff problem. We need to model something with very high resolution for a very long time in both time and space. So why do we want to use DNS? Essentially, fusion reactors are pretty expensive. Probably want to get it vaguely right the first time. But liquid metals are very difficult to do experimental work on because they're opaque and very corrosive. So we can only really have point or line data from them. And essentially, there's a demand for high fidelity, large data sets to train AI models on, as well as traditional CFD models. So onto our methodology. So CHAPSIM2 is a fractional step, finite difference DNS solver, which has been developed by Dr. Wei Wang at SDFC for nuclear applications. It's a Fortran code. We use a projection method to solve our velocity, which means that we solve like an intermediate field, which is non-solenoidal, and then compute a pressure correction step using a Poisson equation, and find a final field by combining those. So we advance our solution forward in time using third order Runge-Kutta, and we solve our Poisson equations with a three-dimensional fast Fourier transform. Yeah, and then we parallelize the simulation using 2D decomp and FFT, using pencil decomposition, which is this bottom figure here. It works on a staggered grid, which is this top figure, which means that our pressure is stored at the cell centers, and then velocity is stored at faces between cell centers. And that means that, for example, when we want to find our pressure gradient, it naturally locates on that face, so we don't have to interpolate and have that numerical error. And yet it's highly scalable. We run case on up to 32,000 cores on Archer 2. So the MHD development is essentially quite simple. We first solve our electric potential fields using our velocity. So we use a 3D FFT to do that, same as we use for pressure. And then we find our electric current density from that field, and then compute our Lorentz force and add that to our momentum equations at the start of each fractional step. And we use Dirichlet boundary conditions for electric current density, and Neumann boundary conditions for electric potential. And this is also implemented on the staggered grid. So our electric potential is stored at cell centers, and current density is between faces. And because the FFT is so numerically expensive, this does result in a slowdown of about 1.6. And so we validated our model against a DNS database that quite a few different MHD codes have used. It's a very canonical layout, so it's parallel plates with a transverse magnetic field, and a very low Hartmann number compared to fusion reactors. So the highest was about 8 here. And I think this figure nicely shows the effect of MHD on turbulence. We see this is on the right, this is with no MHD, to a Hartmann number of 8 on the left. So it effectively elongates streaks. This is a streamwise plane in the buffer layer, which is like near near the wall. And it tends to elongate streaks in the streamwise direction and reduce the intensity of the turbulence. And that's the elongation of the streaks is due to a reduction in drag from Joule dissipation. So that's a sort of indirect effect. So things get a bit more complicated when we go to add heating as well. So this is a finite channel, which means we use a turbulence generator, an isothermal turbulence generator, feed it into a heated and magnetic domain. And this is to look at this spatial instability, spatially developing instability that we have. So the dark region here is reverse flow. The mean flow is down, which means that this is the hot wall of the simulation and the cold wall on this side. And so buoyancy is strong enough in this case to reverse flow on the hot wall, and then streaks come out and sort of explode into the mean flow, as you can see a few points up here. These are very preliminary results. These are fresh off Archer 2 yesterday morning. So yeah. And what I'm really interested in, so this is with a 1D magnetic field, which is what most work has been done on. I want to investigate what happens when we add another component, essentially, and how the inclination of that magnetic field is going to affect our turbulence and the effect on heat transfer, for example. So challenges and outlook. So what we really want to do is develop the capabilities of this DNS code to model everything that we might experience in a fusion reactor in high fidelity, so that we can then use that as a base for more capable, less expensive codes. Not more capable, just less expensive. So I'd like to develop variable electric boundary conditions to model different wall conductivities, and then, yeah, create full field data. And the porting of ChapSim2 to GPUs is being worked on by Dr. Bo Liu, SDFC, so that will allow acceleration of our code in the future. And that's it from me. Thank you for listening.
Thank you very much. I think we've got time for a couple of questions.
Thank you. I'll just, you've got a slightly easier task than looking at a neutron star to actually verify. When I did some of this, there's a I'm going to call it high polynomial node CFD, which is sort of what they're doing, which is quite tough when you've got this transition in the areas. How do you verify this? I know it's easy. I remember doing it. I remember some people were doing it on medical side for the thing, because at least you've got a chance of optically verifying it. You've got easier than a neutron star, but I guess you've got some visualizations to look at.
So we're directly solving the Navier-Stokes and electric equations there. So we know, for example, the MHD solver alone. I look at the electric charge conservation between two insulated walls, which should be 0, which gives us an accuracy of the solver, which is to machine accuracy. So we know if we have enough resolution that the MHD solver alone is accurate. Yeah.
Brilliant. Any other questions? I had a quick question. The results that you just got off Archer 2, the latest ones, look really interesting. I was wondering, what I presume is going to be quite a big challenge going from your nice square sort of 2D domain to this 3D donut and this odd geometry. Do you want to say something about that challenge? Oh.
Yeah, so we are limited in geometry. That's one of the things from using an FFT and actually solving all the equations. So what I'm going to do is vary the spatial, the shape of the magnetic field rather than the geometry, and model it in that way, if that makes sense.
Yeah, that's interesting. Well, should we thank Alex?